Okay, so welcome back to class number 1. Here's example 1. This is the first case, probably the most simple case of the fundamental kinematic relations. And here we go. So we have acceleration of a point is defined by the relation of negative 1.8 sine kt. Right, so that's some constant. This is acceleration that's a function of time. That should be the first thing that jumps out in our mind. That's the thing that we want to look for in the beginning, right? And these are in meters per second squared and seconds. And then k is something that's given to us, right? So this is something that we know maybe from experiment or from some fundamental law. And we know here's some like boundary conditions, we might think of them, where we say when the position's at 0 and the velocity is 0.6, so knowing that at time 0 the position is 0 and the velocity is 0.6 meters per second, we want to find the velocity and position at point A. I guess we're just going to call it point A when the time is equal to 0.5 seconds, right? So we really went fast in our stopwatch apparently. So I like to, when we're doing a problem, I like to write out the stuff that I know kind of separately. That as I'm writing it out, I'm thinking about what's taking place and what I have. And I know that k is equal to 3 radians per second. And I might even note that this is a function of time. And when x is equal to 0, maybe I should start out with t is equal to 0, but that's all right. And v is equal to 0.6 meters per second. So I recognize that this as being case 1, as I've set up here. So acceleration is dv dt, and we rewrite as acceleration times dt, just moving that over here, multiplying by there, and dv, and we want to integrate these, right? So let me substitute stuff in there. So we take the integral from 0, and for the time being, I'm going to use t. Now I know that I could put that 0.5 seconds in there, but I'm just going to demonstrate that this is something that works out pretty well, because we want to know the velocity and the position, right? We want to know the position. So when we want to know the position, we'll see in a second, it's going to make our lives easier to keep that as a variable and not stick it in right away. So we have negative 1.8 times the sine of 3t, and that's going to be dt. dt. So we're going to integrate that, and it's going to be equal to the velocity from 0.6 to v. We're just going to keep that as a variable, dv. And so what we're going to end up doing here, we know that that's going to be, when we integrate, that's going to be the cosine, right? But we have to take like the 1/3 of the thing, right? So we have to take and divide the front part by 3. We also know when we integrate, that's going to be negative cosine, right? So that ends up being a positive right there. So if we divide that 1.8 by 3 right here, we get 0.6, right? Cosine of 3t, right? And that's this one. Then we subtract out 1 from it. We subtract out, I guess I did skip a step, would have been better right here. But what we're going to, now we do that with t, but then we have to do it minus what would happen to 0. And so what we end up finding is subtracting the thing out is, because the cosine of 0 is just going to be 1, we get that 0.6 times that, right? So it's just 0.6. Here you go. Yeah. So make sure that you think that through and understood that way. Okay, I didn't explain that perfectly well. But anyway, this over here is just going to be v minus 0.6, right? And noteworthy, we have a minus 0.6 and a minus 0.6, so those cancel out. So what we're left with is the velocity is equal to 0.6 times the cosine of 3t. So now that's a velocity as a function of time. Do I want to wait for a second or put it in? We could just say that we plug it in. We could say at t is equal to 0.5 seconds, the velocity, which we could also point that right there, is going to be equal to 0.6 times the cosine of 3 times 0.5, and what we end up finding is that it's going to be 0.0424, and these are meters per second. So we've answered part of our question. So now the next thing, because we wanted velocity, we found that. Now the other part we have to have position. So we put in position. Take this guy right here that we conveniently knew ahead of time. Hey, let's make sure one of the steps we take in here is to write velocity as a function of time. Now we could use the velocity is equal to position, which I'll call dx. It doesn't have to be x. This is only one dimensional. We're just going along a straight line right here for the thing. We rewrite that as vt equals dx, right? And now, because velocity is a function of time, we can integrate as a function of time. So we plug the thing in there, and we go 0.6 times the cosine of 3t, right? Going from, let's still keep it as a variable right here. So this is, whoops, I got to be careful here. No, this is time. The 0 time is equal to, again, and that's dt, right? And that's going to be equal to the position right here, which is going to be, we know that this at time 0, the position is 0, and let's just keep this as x right here. So when we integrate this, we end up getting, we have to divide this again by 3, and this turns into positive sign. So we have 0.2, right? We've divided that 0.6 by 3. Sine of 3t is going to be equal to x minus 0. So now we have x as a function of time. And we could go ahead and plug in at t is equal to 0.5 seconds. We could say that x, which we could say right here is 0.5, is going to be equal to 0.2 times the sine of 3 times 0.5. And I believe we get 0.199 meters. So there's the answers right there, right? And what I like you to do in homework is give me the full thing, right? So the velocity of 0.5 at 0.5 is equal to 0.4, whoops, 0, left out 0, 424 meters per second. And the position at 0.5 is equal to 0.199 meters. It's just nice for me to see a box at the end, and just rewrite the thing out, as opposed to trying to hunt for it in the middle. So there you go. There's example 1. It seems pretty easy, right? But the problems can get pretty more difficult quickly. So don't just stop here. Make sure you try harder and harder problems to challenge yourself and become a better problem solver. Thank you.